Okay, thank you, everyone. Our next speaker for this session is Jun Takahashi. Thank you.
Can I start? Okay. Thanks for the introduction. Today I'm going to be presenting about fast mixing quantum Monte Carlo algorithm for the Heisenberg model, or also known as the quantum max-cut problem, on some subsets of bipartite graphs. So this work was in collaboration with Samuel Slezak and Elizabeth Crosson when we were all at University of New Mexico, and we are currently located in different places. Okay, so I'd like to first motivate why we care about this problem. So we had Heisenberg model in the title, but it's actually exactly the same as just quantum max-cut problem, which is basically just minimizing the ground state problem of this kind of Hamiltonian on a spin 1/2 system. And the nice thing about this term of the Hamiltonian is that it's SU2 symmetric, so it reflects the natural symmetry of a qubit. And it's also just a projection to the singlet state, which is a state like this. So this actually is a maximally entangled state. So in order to truly minimize this Hamiltonian, you really need to have a good understanding of entanglement. So in the quantum information community, under this name of quantum max-cut, it's been very much actively in research because it's known to be QMA complete if you want to get the ground state. But the nicer thing is that if you look at the classical counterpart, it has a very nice threshold phenomena where you have a semi-definite programming algorithm that achieves 87% approximation ratio. But if you want to get anything slightly better than that, it's known to be NP hard under the unique games conjecture. So we want to know if there is a similarly very nice threshold in the quantum case or not. And although we have a lot of interesting advancements, it's still very much open, I would say. And I'd like to finally have a motivator where to say that in the condensed matter physics community, it's called the Heisenberg model. And for that reason, so usually condensed matter physicists are interested in this exactly same model because it's like the simplest model you can have for quantum magnetism. And it's very much understood that if you have a square lattice, then the ground state is something close to a product state. But once you move to slightly more complicated graphs like this one with, so the square lattice with next nearest neighbor interactions, then we don't even know what the ground state looks like today. Okay, so it seems like the square lattice case and the other lattice cases are very different. And the biggest difference is that the square lattice is bipartite. So it's easier to see why bipartite graphs are easier if you go back to the classical case. In the classical case, the Hamiltonian is really just a Ising antiferromagnet. And in this case, we again know that obtaining the ground state energy is NP complete. But if we restrict ourselves to bipartite graphs, which in this talk, it really just means that it's too colorable, then the problem is literally trivial. Now, in the quantum case, again, for general graphs, we know that it is QMA complete. But if we restrict ourselves for the bipartite graphs, then there actually always exists this unitary transformation where you can conjugate the Hamiltonian as a basis, which turns this Hamiltonian into a stochastic Hamiltonian, and therefore you don't have the sign problem. And therefore, it cannot be QMA complete. It's contained in StochMA. So as a natural question, people are asking, what is the complexity of the quantum max-cut on bipartite graphs? And this is not only a purely theoretical question, because people actually use the ground state problem of the Heisenberg model for example, on the cubic lattice in order to assess how efficient a quantum algorithm is. But so that's actually exactly what they do in this famous paper. But of course, if a cubic lattice is bipartite, so if it turns out to be polynomial time solvable, then that's not really a good problem to be assessing your quantum algorithm. So I keep on saying that without a sign problem, we can use quantum Monte Carlo, but I quickly just want to go through what quantum Monte Carlo is. So it's easier to understand as so we can first start off when you're interested in a classical probability distribution represented by pi, then the most important thing actually is just this normalization constant. So the fact that you can write this up as a summation of non-negative terms really makes it possible for you to estimate any kind of quantity or the expectation value of that of respect to that weights, as long as, so they don't need to be normalized. But in general, this distribution, it can be complicated, have a complicated structure. So what we do is we consider a Markov chain, which is basically just a random walk. And as long as it satisfies the detail balance condition, which is a technical condition, then after you do this random walk many times, you can be guaranteed that you're going to be in a place with the probability proportional or probability exactly with this pi after this many time steps. And this is exactly what's called the mixing time. And in this talk, I'm not going to really make a distinction with the relaxation time because they're polynomial equivalent. So in the quantum, this was all about a classical configuration. But even when you have a quantum system, if you have some sort of a normalization factor, which usually is the partition function, which is the trace of an exponentially large matrix, you can still, if you can rewrite it as a summation of non-negative numbers, then this situation is exactly the same as the classical case. So you can just consider a random walk on top of this abstract configuration that I just call X, and then if it mixes fast, you can simulate a ground state or a thermal state of a quantum system. And that's what's called a quantum Monte Carlo. And I actually come from a condensed matter physics background, so I've done simulations with like 10 to the 6 qubits. So empirically, as condensed matter physicists, we know that it cannot be QMA complete or even Stoke-MA complete. It has to be something like BPP is our empirical understanding of the problem. So our project was all about trying to prove that intuition, but actually rigorously analyzing this kind of Markov chains is always a hard problem. And we ended up just getting this result, which is a partial result of what we really wanted. So whenever you have this bipartite kind of graph, if you call one side to be A and B sublattice, then if one side, let's call it A, only has log n amount of qubits, then we can show that a Markov chain Monte Carlo method actually mixes in polynomial time. And therefore, the quantum max-cut problem for that restricted set of instances is in BPP. So we can actually also have a little bit of extension of this result. So first of all, we can have some non-uniform weights. We can have, so, you know, as long as they're all positive. And we can also have ferromagnetic interactions, so opposite signs, as long as those interactions only connect qubits within the same sublattice, so blue to blue or red to red. And we can also have transverse field interactions or transverse field terms as well. And within this framework, we can show that it's always going to mix in polynomial time. OK, so how we do that, we need to come up with an actual algorithm that mixes fast. And to do that, what we basically did was that we combined all sorts of different quantum Monte Carlos that were considered in the past by physicists and stitched them together, getting all the desirable properties so that it is easy to analyze while still being actually fast mixing. So in order to do that, what we end up noticing was that we don't want to start from the partition function. We just want to consider something as an approximate ground state by applying the negative Hamiltonian many, many times to a trivial state. So this is close enough to the ground state. And then the normalization factor really just becomes the inner product of this, because obviously that kind of state will not be normalized on its own. So in this case, after a lot of rewriting, we can show that this actually is the same as the summation of this non-negative terms, 2 to the power of number of loops for what we call the bond configuration. So I need to explain what this bond configuration is. What that is, for example, if the graph that you're interested in is a line graph with 4 vertices like this, a typical bond configuration would look like this. So you have vertical lines corresponding to each qubits, and you have these bonds sprinkled around. And in this example, I'm just setting 2b to be 8, so I have 8 bonds in total. And this is a bond configuration, and this is going to have the weight, which is 2 to the power of number of loops, and the number of loops is where it gets non-trivial. So in order to count the number of loops, you can start from anywhere, for example, this red point. Then what you're going to do is you're going to move in the vertical direction along this line, and whenever you hit a bond, you're going to go to the other side as if it's a bridge, and then make a big U-turn. So you're going to come down next until you hit the next bond. So then you're going to get to the other side again, and then so on. So this way you can continue until you end up getting to another edge where you stop. So this is one loop. Although it's technically not a loop, it's just a string, but we don't make distinction in this case. So you can do that starting from another place, and another place, and another place, and these other ones are actually loops, but you can see that all of the graph, or all of this configuration, actually is decomposed into loops. And in this case, you have 6 loops. So this has weight 2 to the power of 6. And if you have a more complicated graph, it's still going to be the same story, but with more complicated structures. But the key point is that you can always decompose the entire configuration into loops, and you're going to have a weight that looks like this exponential base 2. Then we can consider a random walk on top of this kind of structure, where each step you just pick one random bond and then move it to a random position, and then count the loops before and after this move so that you can accept that move with probability that's proportional to those 2 weights. And so this Markov chain is going to be the main our algorithm that we're going to be analyzing in order to answer the question of, can we prove quantum Monte Carlo is efficient for these general bipartite cases? And I'd like to just note here that in general, when we want to ask if a problem is solvable by this quantum Monte Carlo, the negative sign problem becomes a very interesting question, because if you can't rewrite your Hamiltonian or the partition function as a summation of non-negative terms, then this whole framework won't work in the first place. And there are a lot of interesting works done in this, what happens when you have the negative sign problem. But in this case, because of the bipartite structure, we never have a negative sign problem anyways. But the true question is does this random walk mix fast? And this is the hardest part. And it's also actually, I would say, is the core of what Monte Carlo algorithms are powerful for. So the main technique that we're going to be using is called the canonical path method by German and Sinclair. So this, and the details of this is going to get too technical, so I just want to show the intuition here. And the intuition here is that if a Markov chain mixes fast, then all of the configurations in that random walk space should be well connected with respect to that random walk that you're considering. So if these are just schematics, so if you have a 2-dimensional space that you want to walk, and if the random walk only moves you locally, then if the probability distribution looks like this, of course, they're well connected. All the high probability points are, you can move from one to another only going through high probability places. But if it looks like this, that's not the case. From this point to this point, you're always going to have to go through a low probability point. So the canonical path method is basically a more rigorous version of this intuition. And what it asks you to do is that if for all possible pair of configurations that you want to be sampling from, x and y, it asks you to come up with a path that connects x and y. And if that path is reasonable, then you can show that your random walk mixes in polynomial time. And what this reasonable means is that this constant congestion ratio is only polynomially big. And there are a lot of symbols, and unfortunately I don't have time to go through all of it. But the important thing is that it has pi x times pi y here, and it basically has QE term here, which is essentially pi z, where z is some intermediate point. So if you have two configurations x and y, which are both relatively high probability, but if you need to go through z, which is exponentially small probability or something, compared to x and y, then this is not going to be polynomial large. It's going to be exponentially large, and you can't prove fast mixing with that specific path, canonical path. So there are so many different ways that you can consider for what you can have as the canonical path here. But here we are just going to consider the simplest possible canonical path, so if you have two configurations x and y, they're both going to look like this sprinkled bond configurations. What we're going to do is that we're going to change, because we have this one dimensionality, we're going to change one bond at a time so that it becomes what y looks like. So one by one. And this is really just the simplest path that you can consider that connects x and y, because you're just going straight from x to y. And this indeed doesn't work for a general graph like this one, G, where it's a line graph, because, for example, in this intermediate configuration, Z, we will have one big loop that looks like this under this way of counting loops. Whereas in x and y, at this position, we were supposed to have many, many small loops. And in this case, you can actually have order n loops, both in x and y. But now that is becoming just one big loop, which means that when you have 2 to the power of number of loops as the weight, it means you have exponentially lower weight in this intermediate point. So this simple path is not going to work for proving fast mixing for general graphs that includes a line graph like this. However, our central observation is that if we restrict our interest to star-like bipartite graphs, which, as I said, only contains small number of A sublattices, this simple path actually works. So imagine a star graph like this, then a typical configuration would look like this. The important thing is that in this kind of highly imbalanced case, there is going to be so many lines that actually start from the left edge and goes all the way to the right edge. So this one is also like that. And there are some that starts from one side and ends up in the other side, but there are minorities. To be more specific, it's bounded by the number of the smaller sublattice size. So, oops, sorry. This was what I was afraid of, but okay. So the important thing is that no matter what you do in the middle, you're going to have many, many lines that actually needs to pass through left to right because of this topological constraint. And you can say that in the middle, you can only have at most order 1 number of loops if you have order 1 number of A sublattice, and order log n of loops if you have order log n A sublattices. So if you go back to this congestion ratio calculation, if you have at most log n loops here, then that means pi, the weight of this configuration is only polynomial, is still going to be, still can only change at most polynomially. Therefore, we can actually prove fast mixing with the Jerome-Sinclair method. And okay, guess I'm running out of time, but I'd like to mention that, so we were able to prove fast mixing for the case where we have log n vertices on one side. But if this goes even smaller, and if we only have order 1 vertices on one side, then we actually already knew that there is a polynomial time algorithm for calculating the ground state, because there's this Marshall-Lieb-Mattis theorem that tells you that the ground state is in the span of z-basis states that looks like this. Basically, you only need k different upspins, and everyone else is pointing down, and you just have, so basically you only have n choose k different states, z-basis states that you need to consider. So you can do exact diagonalization in that smaller subspace, and that's only going to be polynomial time. So, but that's only true if k is order 1. So we can say that depending on the size of the A sublattice, for the most general case, of course, we want to consider order n number of A sublattice sites, and that's exactly what this open problem is about. But we can say that until now, we only had this trivial result that it's really not trivial because you need this non-trivial theorem to be there. But we can just do exact analyzation if it's order 1. But we can prove that with quantum Monte Carlo, it mixes at least up to log n. But in order to show this, we only used a very trivial application of the canonical path construction. So if we can come up with a more clever path, maybe there are ways to prove the full open problem. And yeah, this is basically it. I'd like to finally mention that so all the extensions that we were able to make, which was with different weights or with X fields and ferromagnets on these restricted cases, they all only act in the favor of the so-called nail order in condensed matter physics. So which I won't get into details, but actually corresponds to a trivial phase in an SUN generalization. I'm very happy to talk about it if anyone is interested in. But the thing I want to say is that maybe this kind of insights from condensed matter physics can further help us to solve the full open problem. So thank you so much for your attention.
Was the Markov chain known in the literature before?
So the specific Markov chain that we used is a stitch work of all sorts of different Markov chains that were considered before. But this specific one, I've never seen in any literature before. But it's, yeah, it's similar to some others.
Hi, Jun.
Okay.
Hi. So it seems that the congestion ratio of phi happens to be a central quantity in your analysis. Mm-hmm. So usually mixing time in MCMC is actually quantified in terms of the spectral gap of the transition matrix. So how is phi related to the spectral gap? Like, do you have any intuition for that?
Yeah, thank you for the question. So, so usually that inverse of the spectral gap is called to be the relaxation time. So what I write, tau relax. And tau mixing is defined in a different way where you can be sure that after tau mixing, you are converged. And these are actually only different by a polynomial factor. So in this case, yeah, I was not really careful about it. So, yeah.
I understand that tau mix and tau relaxation are only different by a polynomial factor. I'm saying that how is a tau mix related to phi, which is the congestion ratio that you have?
Yeah,
or how is the spectral gap related to phi? Like if you were to take the whole transition matrix and take the highest eigenvalue and take the next highest eigenvalue and subtract the two, that will be the spectral gap. So I can sort of say that my mixing time is going to be of the order of 1 by the spectral gap, right? To some polynomial constant. So how is the phi in your analysis related to that spectral gap? So is there any intuition for that?
Yeah, I'm not an expert in that, but I would guess that, like, we can just say the trivial fact that it's again related to the congestion ratio with the same polynomial factor. That's my understanding.
Hey, Jun. So I was wondering, you said for the constant sublattice, like when A is sublattices of a constant size, you said that, I mean, you could use like the Lie-Mattis theory to know exactly the number of upspins.
Right.
Equal. With your approach and when it's log n and you use the quantum, like the Monte Carlo methods, can you still tell does it still obey this like number of upspins is equal to the size of the A sublattice?
Yes, yeah, that is always going to be true because of the Lee-Mattis theorem.
Sure.
But it's simply the fact that that is not going to help you enough to do exact analyzation in polynomial time.
Got it. Okay.
Hi. Do you think you can extend your techniques to like k-partite graphs? Is that possible?
K-partite graphs. Oh, that's a very interesting question. Immediately, no. Like my immediate response would be maybe not, because when it's not bipartite anymore, it's not stochastic anymore. So that's going to be the first obstacle. But at least in the case of three-partite graphs, like a complete three-partite graph's ground state is actually well known as well. And it's the same in a triangular lattice. So maybe there is also a very clever way of dealing those situations. But yeah, that would be a truly new thing, if that's possible.